Hi, and welcome back to part 7 of the Block 74 Apollo Guidance Computer Replica series. Today we're going to take a slight detour. I've started working on the design of the A register, which is the accumulator, and it's one of the first of the more complex registers that we're going to have to design and build. Now, before we can go down that route too far, I wanted to spend a little bit of time talking about the clock for the computer and some of the control pulses and kind of the control mechanism we're going to be using in order to operate the computer once it's all put together. We spent a little bit of time in the last episode talking about the control pulses. So we looked at kind of a document summarizing all of the control pulses within the computer and the different behaviors that those control pulses will trigger. And as we go through that, we need to look at some of those control pulses trigger certain behaviors within a particular register for it to perform a specific option or operation. Some of them are fairly straightforward, like write pulses to write data into the register. Some are a bit more complicated around, performing shift operations or selecting, whether we do a direct address for some of the registers, whether we do a channel instruction, and so on and so forth. And the A register starts to get into a few more of these more complex kind of logic that we'll have to look into. So let's talk a little bit about kind of the clock on the computer. I'm going to move myself over here so we can kind of see what we're doing. So when we design a computer like the AGC replica, the clock becomes really important because it determines when various parts of the circuitry are going to perform their functions. Um, Two of the things that we've looked at most up till now are things called the read timer or the RT signal and the write timer, the WT signal. Now, the read timer is basically the timer that when we use our logic and we AND it or OR it with a control pulse, is when we look to kind of push data out onto a bus. So you can kind of see here kind of a little clock uh, uh, kind of timeline here that shows the different clock signals that we've got going. And what we've done is we've kind of looked down here is this is actual one of the timing diagrams from the Apollo guidance computer itself. And a lot of the reasons why we have to have this sequencing and why it's so important is we have a common shared bus. So we have the WL, the write lines, and we have to kind of synchronize when are we pushing data onto that bus, when are we reading data off of it, and making sure that everything kind of stays organized and occurs in sequence. And making things a little bit more complex is that electronics and gates, of course, aren't instantaneous. There is a little bit of delay as the logic kind of works its way through the gates, through ROM chips, through multiplexers, through all of the different components that make up the computer. Now, fortunately, the AGC is a fairly slow computer by modern standards. So the logic, the 74 series logic that we're using in comparison to the clock speeds that we're dealing with. So the original AGC was a 1.024 megahertz computer. So very slow by modern standards. So we don't have to be as picky when it comes to clocking versus if we're designing a modern computer or modern processor where the processor is running so fast that it actually takes measurable or significant amount of time from a clock perspective for logic to propagate from one end of the processor to the other. So if we look here, kind of the way, and there's a bunch of other timing pulses and signals that the original AGC developed. One thing we'll get into in later is some of the timers or what they call the divider. That there's a bunch of almost clock signals that are used for measuring the amount of time that has passed, and there are certain interrupts that are generated, after a certain amount of time. Some of that is for real-time clocks, so you can actually have a real, hours, days, mission elapsed time in the computer. But for right now, we're just going to look at kind of here's the basic clock, and this is kind of the 1 megahertz clock, and kind of pulsing, every fraction of a second. And then we've got a couple of different kind of timers or sort of pulses that occur in order to control the functioning of the computer. So here is the CT. This is the clear timer. And because of the way that the AGC implemented the kind of storage elements through interconnected gates to perform flip-flops, there's actually a clear signal that they need to apply. So every register before it's written into would be cleared. So you can kind of see this timing is we've got this clear pulse that would clear the register, and then we have our write pulse that would write data into it. So we're always writing into a clean register. We also have our kind of read pulse, which is when do we place data onto the bus? So if we kind of look at the sequence, we'd say, okay, first we need to clear a register. Then we need to get ready to write to it. And then we need to actually place data onto the bus in order for it to actually, so the registers are ready to receive the data. We push the data onto the bus, and now we kind of write that data in. Now, because of our logic is a little bit different, and the way that we're kind of running our computer is, not the individual gates. We're using actual registers that have clock pulses. It's important to understand that certain logic will be triggered on a rising edge of a clock, and some will be on a trailing edge of a clock when it's triggered. Most of the logic that we're using is going to trigger on the rising edge, and that just kind of makes it simpler for our own purposes, but it is something to be aware of. So the way that we've implemented things on the replica is right now I'm using an 8 megahertz main clock, so 8 times faster than the computer would operate. And the reason that I've selected 8 versus just using a 1 megahertz clock is, as I've started some of the preliminary design of the memory register, the G register, there's some interesting shift, what they call edit functions, where as data is written into or out of the G register, we can shift the data either to the left or to the right, and we may need to kind of perform multiple operations within a single computer clock pulse in order to kind of replicate that shift register. So that's why I've picked an 8 megahertz clock, and then we'll get much more into that as we look at the G register. So first, what I do is I divide that 8 megahertz clock in two to produce a 4 megahertz clock. And then I use sort of interconnected JK flip-flops to produce an overlapping 4-phase 1 megahertz clock. So this is kind of like what it looks like here. We've got my little clock 8 signal. So this is our 8 megahertz clock going across the top. We divide it in two to produce this 4 megahertz clock. And then we have kind of these 4 phases. So we've got kind of one phase here that kind of goes first. So this is the clock 1, and this is, 1. So this is 1. So we've got our, kind of half pulse here. And then we've got our next one, which is basically shifted over by half a clock signal. So this goes positive, and then halfway through, the next clock goes positive. And same for the third one. Halfway through the second one, it goes positive, and then the fourth one goes positive here. So that's basically, each one kind of overlaps a bit as we kind of go through this sequencing, and that allows us to generate both our kind of our read timer and our write timer. So what we'll do is we'll start with basically we need to read data onto a bus. So we'll have our low clock, and then suddenly the clock will come up. And based on the other control pulses we have at the time, for example, a RZ, for example, we would then say, okay, the clock is now going positive. The RZ signal is being asserted. That means we're going to read that data from the Z register out onto the bus. So the data is basically going to be on the bus for this duration. And then halfway through, we're going to initiate our write timer. And that might be another pulse that's kind of been asserted at the same time, say RB, or sorry, WB. So write the B register. That means that, okay, this goes positive when we have the data from the Z register on the bus. We get the write signal, and that means we'll basically load that data into the B register. So this kind of using these two pulses right here allows us to kind of sequence our pushing data onto the bus and then pulling it off the bus. And it gives us a bit of time for, logic to kind of propagate through the system and signals to settle down as we kind of go through each sequence. And then we've got these other two, clock 1 and clock 4, that I've labeled, that we may use for other things. And there's actually some, as we get into the next session, we'll talk about some of the other clock pulses I've had to generate in order to deal with some interesting behavior that I've learned kind of along the way. So that, if we kind of look at how that kind of translates into kind of the circuitry itself, here's kind of the sequence, the kind of clock that I've built out. And if you go to the Ben Eater videos where he designs and builds a clock, a lot of this is going to look fairly similar, right? So I have here is the 8 megahertz oscillator, which generates my 8 megahertz signal. And then we've got right here is our divider. So this is kind of divides the clock by 2. And then we have a couple of different options that are going to help us debug the computer as we build it. So we've got our, what I'm calling sort of a step versus clock selector. So this is basically if we select step, so basically a switch, that'll allow us to use a kind of pulse. And down here, we've got a little bit right here, basically a step clock. So basically, I can manually advance the clock 1 pulse at a time. And then if I use it to like an actual like clock that's running, I have the option to either do what I call the fast clock or the slow clock. So the fast clock will be the 8 megahertz clock. That'll be what we'll use when it's running normally. And then the slow clock is I have using a 555 chip here. I basically got an oscillator, a variable oscillator. So I have a 1 meg potentiometer that I can use to basically slow down the clock so it can still run in kind of a automated fashion, but at a much, much slower rate so that we can actually see how things are going to propagate. And then this logic in the middle here is really just, how do we select which of these sources, the 8 megahertz, the manual clock pulsar, or the fast or slow clock. We also have a halt control signal that we're going to use. That basically, if whatever reason the computer needs to basically stop the clock, we have that option. And then we have our kind of 4 megahertz divided clock that comes out here. And then these are our 2 interconnected JK flip-flops that produce the kind of the 4-phase clock here. One thing that took me a little while to kind of debug a little bit is the 74LS109 is a J not K flip-flop. So this K is actually inverted, which in some ways makes it easier because there's certain ways that we want to interconnect these gates that before we'd actually have to do inversions and use Q versus Q bar. This actually simplifies it so we can use a couple fewer inverters, but it took me a little bit of troubleshooting to understand why my clock wasn't working, because I first assumed this is just a JK flip-flop, that this input wasn't inverted. They should probably have a little circle here where they show that it's actually an inverted input as opposed to just a normal input, just kind of like you have here on the 555. The other circuits here, this is just a debouncer circuit for the push button. So that way, when we push the button to manually advance the clock, we only get a very, very clean single pulse, which makes it easiest for us to step through. And then I've got a few more kind of debouncers for the fast slow clock switch and the step clock switch as well. And that provides our input for our step clock. Here I've just got a little kind of simulator running, and that's actually where I generated the timing circuit from. There's a few other clocks, like I said, that we'll talk about here, where I've got this kind of RA and RC and D latch, and that we'll talk about in our next video, because it's again where things start to get a little bit more interesting. Okay. So what I'm going to kind of switch to next after the clock is a little bit more around some of the control pulses. Well, actually, sorry, first I'll just quickly talk about kind of the bill of material. So here's a picture of the kind of the clock circuit on one of my boards. I use this board also as kind of the start of my control circuit. So all the EPROMs for generating the control pulses are on this side of the board. You can kind of see the blue wires, but the rest is here. So I've got my 8 megahertz oscillator. I'm using a total of 4 555 timers, one to actually generate the variable clock, and then the other 3 as just debouncers. I've got my D-type latch or D-type flip-flop in order to use it as a clock divider, and then my JK flip-flop to provide that 4-phase clock. And then the logic to combine them together. I've got my hex inverter. I've got some NOR gates, some AND gates, and then a buffer just to buffer the clock that's being generated. So again, we've got a good clock signal to distribute throughout all the rest of the components. Some other kind of non-digital components just to support the 555. So we've got some electrolytic capacitors, some ceramic capacitors, some resistors, the potentiometer for the variable clock, and then a few switches. And then I've also added a blue LED and 4 yellow LEDs that just kind of, the blue LED will flash every time there's a clock pulse, and then the yellows are each synchronized to one of the 4 overlapping phases of the clock. So I can see whether we're in kind of 1, 2, 3, or 4. And I'll record a video probably in the next week or two that will actually show some functioning of the computer where we can actually latch data from one register to the other. Next topic is kind of the machine instructions and control pulses. So this is where we start getting into a little bit more on like, how does the computer, the AGC itself, work? So we talked about kind of this list here on the last episode, where we talked about a number of the different control pulses. And so we've got here, one is like RB. This is where we read bits out onto the right lines. There's a few others, like for example, here R6. This will enter a constant. So in this case, octal 6 onto the right lines as an address. There's a few others we've got along the way, but this is our list of control pulses. Now, of course, the computer itself doesn't, when you program it, you're not programming individual control pulses. You're programming it using machine instructions. So here's a sort of a subset of the Apollo guidance computer machine instructions. So they've got here, transfer control to K, exchange data with location K, clear and subtract data. They've got add. Here we've got what we call some extra code instructions where we can do subtractions, multiply, divide, and a bunch of others. Now, what's kind of interesting is as they designed the computer, so we're building a Block 2 Apollo guidance computer. There was, before that, the Block 1 Apollo guidance computer. Now, the Block 1 was only used on unmanned missions, but it was simpler than the Block 2. And one of the improvements that they made when they made the Block 2 was to introduce a number of additional instructions. The Block 1 had a very limited instruction set. Now, in order to do this, they had to kind of shoehorn the data, the additional instructions into the computer so that it'll kind of function correctly. So this is one thing that kind of added a little bit more complicated is that when the AGC writes an instruction, it's basically a single instruction. So the op code or the machine code, the operator code, and that's these kind of, they call it order code here. And then there's what are we going to action that particular code on? So for example, we've got transfer control to K is we would say, okay, well, we need to have in this case, our op code of 00. And then we need K. We need the actual data of where are we going to transfer control to, or we want to mask, which is a logical and with data from K. Now, K could be a memory address. K could be one of the directly addressable registers. There's a few K, sources of what K could be. Now, we've talked about the way that the Apollo guidance computer is a 16-bit computer. And the reality is it isn't quite a 16-bit computer. So the memory, the ROM and the RAM are 16-bit. And the ALU is also 16-bit, so 16 bits wide. However, in memory, one of those bits, bit 15, is the parity bit. So it's used to verify that the data that's being transferred from memory is in fact accurate, that it hasn't been modified or impacted in some way. And that makes a lot of sense if you think about the Apollo guidance computer and kind of the environment it's in. So not only is it a computer that is running the spacecraft, which is keeping 3 astronauts alive. So it is a kind of mission critical device, but it is also passing through like the Van Allen belts when it leaves Earth orbit. And, there's, solar storms and potential, outside impact from, cosmic rays, high energy particles that could potentially flip a memory address, as well as the rope core that's kind of being used is potentially susceptible to some of these external influences. So this parity bit allowed the computer to verify that the data I'm getting back from memory is what I expect. Now that means that from a memory, when we're bringing in data, from like an actual instruction from read-only memory, is we only have 15 bits to work with, and a memory address is 12 bits. So we've already basically taken our 15 bits minus 12. That only leaves 3 bits, which gives us 8 different options. Now, 8 options for an instruction is pretty limited. You can't really build a computer effectively with just 8 instructions. And that you can see the basic instructions. We've got this list, and these are the 8 instructions that are kind of just the basic within the computer. So the first thing that they did to kind of shoehorn some additional instructions is they added this extra bit called the extend flag, where you use basically there's this ext control pulse where you can actually assert it to set this flag, which gives you an additional bit. And these basically another set of 8 instructions called our extra code instructions. So this is where our subtract, multiply, divide, and so on are added. We also have a case of what they call these quarter code instructions. So not every instruction requires a full 12-bit memory address. Some require less than that. So in some instructions, they actually steal 2 of those bits, these kind of quarter code bits, to provide an additional set of instructions that operate without the need for a 12-bit memory address. And then for channel and interrupt instructions, they steal another bit so that they only leave kind of 9 bits for the what instruction we're actually going to execute this particular item against. Now, you'll notice here that we got, okay, what are the execution times in MCT? So this is kind of machine control timers, and that some of these instructions are very, very simple, and some of them are very, very complicated. So if you look at divide, it actually takes like 18 MCTs to run versus some of these others, which are very, very, 2 or 3. So as we kind of run each of these instructions, and I'll show you this in just a moment, they can break down each instruction into basically they've got a 3-bit stage counter, which allows us to kind of, for some of these more complex instructions, to break them up into a variety of different sub instructions that are assembled to form an actual machine instruction. And then each sub instruction has 12 actions that I can take, basically T01 to T12. Now I'm going to move to the next slide, and this is where it all kind of comes together, where we map these instructions, these machine instructions, to the actual control pulses. And if you've gone through Ben Eater's video where he creates the control EEPROM for his 8-bit computer, you'll basically, this is going to look very familiar, but this is from the Apollo guidance computer documentation. So there's about 10 or 15 pages of these different diagrams within the AGC documentation. And what you can see here is we've got an instruction or sub-instruction, in this case STD2. We've also got TC0, TCF0, CC0, BZF0. So these are all sub-instructions. And these are that 7 kind of bits that I told you about that kind of go together to form the particular opcode. So we've got here this 0, you can see here, this is our EXT, this is our extend bit that we talked about. And then we've got our 3 bits for our kind of opcode, right? So this is our TCF 001. We have our 2 bits here. This is our quarter codes that we talked about. So instructions that don't require the full 12 bits. And then we've got our additional bit for the channel and interrupt instruction, so that a instruction can have up to 7 bits to indicate which one it is. Now, in this case, TC0. Now, if we go here, if we just go back, this is our TC. So this is we needed the full 12 bits of memory, of data for a memory address. So you can see here, we're only using 000, which is the 3 bits that we have as part of our sequence register. And then we don't really care about the other bits, because this is actually going to be a memory address, or the 3 high bits of the memory address that's associated with this particular instruction. For TCF0, this is a quarter code, so we don't care about the last one, because that's being used by one of the address, or the high bit of the address, and then so on and so forth. Now, some of these, this is where I talk about kind of the stage, in that some instructions basically they operate within one stage, right? So that they basically they're able to complete their full instruction within one kind of 12 set of actions. Others are like they require multiple stages they need to go through in order to complete that instruction. So this STD2 is actually a sub instruction that pops up a multiple number of times, because it basically advances the computer to the kind of the next instruction. So you can see here, it's actually like, oh, well, these are all X's. So it's basically, it means that every single instruction within the Apollo guidance computer at stage 2 will automatically have this STD2 sub-instruction. And that's basically where it's going to increment our program counter and load the next instruction from memory, so that basically it advances to the next instruction as the computer operates. Now, you'll notice along here, these initials, these are our control pulses. So as we go through to say we need to execute a TC0 instruction, we can say, okay, in basically T01, so time 0 action, we need to issue a RB pulse. So basically read the contents of B onto the bus. We need to do a WY12. So that's actually data that we will write into the Y register. And in fact, this control pulse writes in the low 12 bits, which is a memory address, right? The 12 bits for a memory address. So we basically take whatever our contents were in B, we take the 12 bits that we need, which are a memory address component. In this case, the CI is clear a carry bit, so that basically we're clearing it, so we're ready for the next instruction. And then we do a few things. We do a RSC and WG. So basically, we want to be able to write data into the G register, which is the kind of the memory, and then we do nisq, which is another command that we'll talk about. It's a little bit more complicated. And then we do our RZ. So we want to, read data into our Z register. We want to write. So basically this takes data from our Q register and writes it into our Z register. But basically this is the mapping of this sub-instruction into all the specific control pulses that have to be issued at the right time in order to provide the actual mechanism of the instruction itself. So this is how that instruction executes. Now you'll notice here we've got, these ones are pretty straightforward. Okay, they just these pulses. As the action timer goes through its sequence, it's gonna at 1 do this, 2 do this, 3 won't do anything, 4 won't do anything, 5 won't do anything, 6 do this, and so on and so forth. Now here we've got these little triangles with 1, 2, 3, 4, and the notes that are associated with if BR, which is the branch registers, equals 0, then we basically follow these. We do RZ at WY12. If it's 2, if the branch register is 1, we do RZ, WY12, and PONX, which is basically put 1 into X. If the branch register is a 2, then we do this. If branch register is 3, we do this. And the branch register is actually 2 bits, so you can have 0, 1, 2, 3, and that's how we kind of do branching within the Apollo guidance computer, which is an important function to make a computer Turing complete, is that we can do branch and basically conditional instructions. And the way that the kind of computer does that, as you see, there's these little commands like TSGN, TPZG. These are actually tests. So this is an instruction where the computer will say, I believe this one is test to see if the contents of G is 0. So if G is 0, it'll write a certain value into the branch registers, and then that'll determine, okay, what action I should take. So this might be, if it's 0, write a 1 into bit 1 of the branch register. This one, I believe, is to check to see if G is negative, so TSGN. And then if it's negative, it writes another bit. And so this is basically how we can get a lot of functionality with just 2 branch register bits. So on a more modern processor, you might have a whole bunch of different flags, like is the contents of the accumulator 0? Is the contents of the accumulator negative? And then, based on that, you can perform branching. In this case, the AGC just uses those 2 bits, and then they can be set depending on different tests that are run by, or basically that the computer instructs to run at previous sequences. So this is a bit of a primer for the, again, how we map the kind of the instructions to the sequence of pulses that goes through. So one really good document that kind of brings a lot of this together, you can see I've got a lot of different documents open right now, is actually I may not have this one, as I'll put actually here it is. This is basically the full list of all the different kind of control pulses that, and kind of the instruction set generated at various times. So you can see here we've got things like DV7, DV6. So these are divide instructions. You can see the stage counter is 7 or 6. There's a little bit of with divide, that the way it kind of works is a little bit more non-intuitive. We use this little stage control pulse to kind of play around with our timing signal. That's another thing for another topic for another episode. But this is a really good kind of document that kind of details all of the different kind of sub-instructions, how they map to the control pulse. And if you actually go far enough into the document, we have all of these different kind of just logic flows, where it basically says, okay, here's a particular instruction. So this is sub-instruction CCS0, and you can kind of visually see, okay, where is the data moving? So in T1, there's the RL10BB pulse and WS pulse, which basically means we want to read data from our B register, and we're going to take it and push it to our S register. So this gives you a bit of a visual of, okay, how is the data actually moving through the system based on the kind of the functionality of what it is that we're trying to do. So that's it for today's session. Next time, we're going to get into the A register in a bit more detail. And some of these, what we've covered today, are going to start playing a much more important role in how we design our A register. So as always, please send me feedback. Always want to make these videos better, more instructive. If there's anything you want me to cover in more detail, please let me know. And click subscribe so that you know when the next video that comes out, so that you can kind of keep along as the project develops. Well, thanks everyone, and I hope everyone has a great rest of the day. Thank you.